Hello, Science 20s. Our lesson today is going to be on electrolytic cells. This is very different than voltaic cells, so please pay attention and make sure that you treat these as two separate topics. You'll notice that this slide is the same as last week. You'll notice that last week we did the voltaic cell, where we had two electrodes, two solutions with some sort of salt bridge, some sort of porous boundary, and we were able to take these chemicals and turn it into electrical energy. Well, today we're going to do the opposite of that. Today we're going to have a non-spontaneous reaction that we're going to call an electrolytic cell. And for this reaction, we're going to need to have some sort of battery. And this battery, this electrical energy, is going to be what causes us to be able to have a chemical reaction. Without this battery, without this energy, this reaction will not actually go. So, by far, the most important part of an electrolytic cell is its definition. This is a device that continuously requires electrical energy. It requires some sort of battery source to produce a chemical reaction. This is because this is a non-spontaneous reaction. So in this reaction over here, this is the Hoffman apparatus. In Science 10, you use this piece of equipment in one of the demos or labs that we did, where there would be a battery hooked up here. So we are supplying a voltage, and we are forcing electricity up and through these electrodes. Here's an electrode, through, here's another, and we're completing the circuit, and this in turn will cause this reaction to actually go forward. And what you see in this reaction are bubbles producing on both electrodes, bubbles coming up from one electrode to collect hydrogen gas, and bubbles coming up from the other electrode to collect oxygen gas. This reaction only works if we supply electricity. Now, like in a voltaic cell, there's a basic design to this. All electrolytic cells are the same for some parts. Now, they might look differently in how we put these in a container or whatnot, but all electrolytic cells still contain two electrodes. There's still two solid electrodes. So we have one platinum electrode right here. We have another platinum electrode right here. Now, the difference in an electrolytic cell is there's only one electrolyte. There's one solution. So we put some sort of ion water solution in the top, and when we pour it in, this solution travels and fills up all of this container, including covering the electrodes. So it's one solution, two electrodes, compared to two solutions, two electrodes that we had in voltaic cell. The other big difference is you'll notice we need a power supply. Because this is a non-spontaneous reaction, it requires energy for it to occur. Therefore, we have to pump through electricity by putting in some sort of power supply. Now, I said before that this has a cathode and an anode. And so I'm going to grab a pen here. And it does have a cathode and an anode, but I want you to notice one big difference. The cathode is negative. That's a big deal. When we did a voltaic cell, cats were positive. They made Mr. Kemp smile. That is not true for an electrolytic cell. It's negative cathode, huge difference, positive anode. Now, that's the only difference. My cathode is still going to be where reduction takes place. My anode is still going to be where oxidation takes place. The reason why my cathode is negative, and it leads to the next slide, is in my power supply, remember, there's a negative side of a battery and a positive side of a battery. And so when I hook it up, I always hook up my negative side close to the cathode. And the reason for this is, remember, a battery produces electricity, and that electricity is what drives this reaction. Electricity is a pile of little E minuses. So when I put these little E minuses in here, they are coming out the negative side of the battery. They are coming out and traveling along the wire on this negative side of the battery, which means they get to the cathode first. So at this moment in time, the cathode, because it's getting hit with the negative electrons first, the cathode is more negative than the anode. Hence, the cathode is negative and the anode is positive. And these electrons then just flow around and it completes the circuit because, again, both electrodes are in only one solution. And electrons are going to flow all the way around from cathode all the way through. But you'll notice, and we'll do this on the other slide here. I'm going to clear this. Oops. But you'll notice when I do this that because the battery is pumping up these negative electrons, so we got these guys going this way, electricity still flows alphabetically. It's still flowing from anode to cathode. It's still flowing this way. But the thing that changes is it's flowing this way because the negative side of the battery is pumping out negative electrons to the cathode, and that is what's making the cathode negative at this moment. So it's still flowing from anode to cathode. So if you want to remember Mr. Kemp's goofy rules, oxidation is still where the anode is. Reduction is still where the cathode is. Goofy rule number 1. Cathode is now negative, anode is positive. That's a change of rule. Okay. Electrons still flow alphabetically from anode to cathode. Rule number 3. Goofy rule number 4, in this solution, because it's more than just water, I usually dissolve something else in here because if I don't dissolve something else with ions, electricity won't flow through it. So we also put in the water sodium sulfate, some sort of electrolyte with ions. And so that allows my electrons to bounce around. Well, that means that my cation that's floating around in here is still going to be attracted to the cathode. My anion, my one solution with anion, it is still attracted to the anode. So cation still goes to cathode, anion still goes to anode. The only difference is cathode is now negative, anode is now positive. And again, in certain examples, the cathode does get bigger, the anode does get smaller. In this example, neither the electrodes will get bigger or smaller. These are special electrodes. Platinum is kind of special, but it's past what we have to understand in Science 20. So I want to look at 3 reasons why we use electrolytic cells. It's easy to justify why we use a voltaic cell. Voltaic cells are batteries. We need batteries. But why do we use electrolytic cells? Why do we use batteries to get a chemical reaction to take place? Well, there's lots of reasons, but we're going to look at the first 3. So one of the reasons is so we can separate water. You saw the Hoffman apparatus in the previous slides. This is a different way to see it. Again, we have a solution in here of water, and it's acidified. It's got ions in it. And so we still have 2 electrodes. We have the anode, and remember I said the anode is still where oxidation is going to take place. We also have our cathode. This is where reduction is going to take place. We have our battery negative side over here. So since this is the negative side of our battery, our electrons are going to flow this way towards the cathode. Because they're flowing towards the cathode, we know the cathode is negative because at this moment in time, it's more negative than the other side. The electrons flow through this all the way over here to the anode. The anode is positive. And so the electrons just flow back all the way through, and we have a complete circuit. This reaction, this energy we put through here, allows the water to break up into oxygen gas and hydrogen gas. I want you to remember, a cup of water is not going to break into its elements. When it evaporates, it's still evaporating as water gas. We're breaking this into hydrogen gas and oxygen gas. That is very different. So we need to supply energy to decompose water into its elements. Well, let's look at another example then. So that's the electrolysis of water. Another example we might do is we might want to look at the refining of copper. So there's different levels of copper. There's pure copper, and then they degrade as you go down so that you can have a mixture. The better the quality of copper, the better it conducts electricity and many other things. So in this picture, you will see again, 1 electrode, cathode, which means it's going to be negative. Two electrodes. Here's the anode. It's going to be positive. And we have a power supply. Need to have a power supply. So since this is the negative side of my power supply, as you can follow the picture, electrons are going this way into the cathode. That's what made it negative. Again, this side is going through reduction because consonant, consonant. This side is going through oxidation, vowel, vowel, anode, always where oxidation occurs. And what you notice is, along with the two electrodes in one solution, you're noticing that as this breaks down, as my anode gets eaten away, lots of things are falling out of this. Because remember, this is impure copper. This is a chunk of copper with many things mixed in with it, gold and silver and platinum. And these guys are just falling to the bottom as sludge, as waste products. Well, the thing that's in here that isn't being wasted is the copper 2 ions. They are reacting and plating onto this, and you'll notice that cathodes, cats, Garfield, still gets bigger in an electrolytic cell. Cathodes get bigger, anodes are still going to get eaten away. And this is what's going to happen. So let's take a look at our actual half reactions for this. And you can see that this copper ions that are now floating around, they are plating themselves onto here. And so we're getting more and more of our pure copper cathode, and this guy's getting bigger. My anode is getting eaten away, and anything that's not a copper 2 ion is just falling to the bottom. This is where, of course, my oxidation is occurring. I know this is oxidation because it is losing electrons. Notice the half reactions, losing electrons. I know this is reduction because it is gaining electrons in the example. The very last reason to do electrolytic cells is electroplating. Now, electroplating is a way of covering the surface of an object with a thin layer of metal. We could do this for covering, let's say the example in here, we have chrome covered bumpers or chrome covered steering wheel, all the shiny parts. We could have, let's say, utensils that are silver, beautiful silver utensils. They are shiny, but again, silver is kind of soft, so you don't want to be eating a bite of turkey and you look down and the tines from your fork are missing. So they might use iron, something stronger underneath, and then put the electroplate, the something shiny like silver over top. Same with, they might do like the chair legs in my classroom. They might use something stronger for the legs, but then put something shiny with different properties on top, like aluminum, so we get a different look to it. Well, to do this, I want us to think about this for a second. Again, I have my battery, different type of battery. Small line on this battery means, oh, I goofed, so we got to go back a page. Small line on this guy means this is the negative side of the battery. This is the positive. So the electrons are flowing here, which means this is the cathode. Cathode is negative, which means the cathode is the thing that's going to be built up. As we have silver nitrate solution, right? We have silver ions and nitrate ions floating around in here. Because this is my cathode, my spoon, which is an iron spoon, it's going to get bigger and it's going to get plated on with silver. And so we're actually putting a nice, beautiful, shiny, expensive metal over top of a strong inner core metal so that I still have the strength of iron, but I have the look of silver. Over here, this guy is going to get eaten away because he is my anode and he is positive, right? And so we're putting these iron ions into the solution so that these iron ions can plate and go from ion to solid and plate on here going through reduction. Now, the last thing I want to talk about when thinking about this is one more application of electrolytic cells are rechargeable batteries. They function as an electrolytic cell when they are actually being recharged, meaning when we are pumping electrons into them, we use these to pump the electric current to force oxidation and reduction to go back to the original reactants.